for example, rational F subs. So first, I would like to explain the background of causability and the CSCK problems on vibrations in Kähler geometry. And second, I would like to give the precise definitions of causability, log-twisted causability, and adiabatic causability. And third, so I would like to state our main theorems and prove these. So prove them. And finally, so we would like to apply our main theorems to causability of rational subsets and explain Miranda's conjecture on causability of rational wireless loss vibrations. So first, so it is one of the most important problems in Kähler geometry. So when the polarization variety XL has a constant scalar curvature Kähler metric omega in C1L. So constant scalar curvature Kähler metrics. So CSC metric. So namely the constant scalar curvature. This is in general C infinity. This is in general a C infinity function. And so blow up of P2, one point blow up of P2 has no CSCK metric. So this is so difficult problem. And so analytic. On the other hand, causability is a notion of pure algebraic geometry introduced by Tien and Nelson. And the following YTD conjecture below predicts that so XL is K-poly stable if and only if there exists a CSCK metric in C1L. So this conjecture predicts that so the existence of CSCK metric is a purely algebraic condition. And in final case, the conjecture is solved by Chen Sun and Tien independently. But for general varieties, this conjecture has not been solved yet. On the other hand, so causability is a purely algebraic condition. So there is a natural question that so could we characterize K-stable varieties in a purely algebraic way without using test configurations? And test configurations, so for test configuration, the definition we will define in section 2 test configurations. So, but so the problem, so Odaka so studied the problem at first. So let XL be a prime normal variety. So then if X is not log canonical, then XL is K unstable for any polarization. And if Kx is numerically trivial and X is gamma log terminal, then XL is K stable. And if L equals to Kx and X is log canonical, then XL is K stable. And for final case, so Fujita Odaka so gave numerical invariant, delta invariant. This is a purely algebraic. And later, Brown and Johnson proved that so X minus Kx is K semi-stable if and only if the delta invariant is bigger than or equal to 1. But for other polarized varieties, so are there any simple criteria for causability without using test configurations? this is an open problem for trivial fibrations and fun fibrations and blow up of k-stable varieties. And so these fibrations appear in variational geometry naturally. So for example, eta fibration and mole fibration. But so CSCK problems of fibrations are studied in Kerala geometry, and to state their results, so we need the following notions: CM line bundle introduced by Paul and Tier. So let F be a fibration of polarized varieties. So the CM line bundle LCM is defined on C as the following Q line bundle, where n equal to the relative dimension of F, B is the general point of C, and mu is the slope. And so we introduce the following condition. So stir semi-positivity of Kc plus LCM. CSK problem on fibrations in Kerala geometry are studied by Fine at first. So Fine proves the following theorem. So let F be a smooth fibration of polarized smooth varieties whose fibers and base have the discrete automorphic groups. If F satisfies the condition stir and all fibers have CSCK matrix, then X epsilon H plus L has a CSCK metric for sufficiently small epsilon. And later, Devon and Sexton generalized Fine theorem by using adiabatic limit argument and optimal simplex connection. This is a class of metric on fibrations they introduced. And they also conjecture that so the existence of an optimal simplex connection coincides with fibration stability they introduced. This is a purely algebraic condition, and so as K stability, but I will not explain deeply today. On the other hand, so Janson proved the following theorem. So let F be a trivial fibration, and so this might have a singular fiber. And if Kx is numerically equivalent to Cl for some positive C, then X epsilon H plus L has a CSCK metric for sufficiently small epsilon. And we mark that, so for trivial smooth fibration, so the product of CM line bundle or equals to the relative chemical divisor. So if the trivial fibration has smooth fibers, the Janson theorem follows from the Fine theorem in this case, when trivial fibration is smooth fibration, is a smooth fibration. And so Devon and Ross prove the following necessary condition of existence of CSCK matrix on fibration of polarized varieties. So let F be a fibration of polarized varieties if X epsilon H plus L is K semi-stable for sufficiently small epsilon, then C LCM L is twisted K semi-stable. And we will explain the definition of twisted K semi-stability in section 2. And so there are natural questions on K stability of fibrations. So the first one, so is there any purely algebraic criterion for K stability of fibration? Fine Darma-Sextona and Janson theorem. And the second, so when Kx is non-nef, does Janson theorem hold? So for example, rational surfaces have chemical line bundle, non-nef. Also, we study Caviar vibrations and obtain the partial consequences we will explain in next section. And here we remark that so we can prove K-stability of KLT minimum models adiabatically by applying the J-stability result of Gaussian. And so this fact is proved in my first preprint. And so this theorem, this fact does not hold when the case when LC minimal models. Next, so I would like to give the precise definitions. So a test configuration carry X carry L for polynomial pair X delta L is a flat, proper, semi-ample, and C-stage invariant family over C with general fiber XL. So carry X carry L looks like so this. So the general fiber coincides with XL, but central fiber degenerates in general, and the carrier is semi-ample. So then we can define the Donaldson-Stark invariant of carrier X carrier L as the following n+1 dimensional intersection number. And here, delta carrier X is the closure of delta times sister in carrier X. And we can define similarly J energy functional as follows. So let H be a line bundle. The non-Archimedean JHNA energy of carrier X carrier is the following n+1 dimensional intersection number. And so now we can define X delta L is K-semi-stable if the Donaldson-Stark invariant is non-negative for any test configuration, and uniformly K-stable if there exists a positive epsilon such that the Donaldson-Stark invariant is bigger than or equal to epsilon JL for any test configuration. And the definition of J stability is of similar form. And here, JL is a norm in the sense that JL equal to 0 if and only if carry X carry L is almost trivial. And this is a non-negative functional. And carry X carry L is almost trivial means so normalization coincides with product with GM trivial option. To experts, so this notion is more familiar than JL. And it is known that so the Donaldson-Stark invariant can be decomposed into the summation of HNA delta and JKX plus delta non-Archimedean energy. This is called non-Archimedean entropy. H is deeply related to the log discrepancy in MMP as follows. So let us recall the definition of log discrepancy and the singularities. So let X delta be a log pair, F be a prime divisor over X, and sigma be a birational morphism such that F is a divisor on Y. So then the Roberts discrepancy of X delta with respect to F is X delta F equal to order of KY plus F minus sigma star KX plus delta with respect to F. And then X delta is commutative terminal if X delta F is positive for any F, and log canonical if X delta F is non-negative for F. And so the following is proved by Odaka. So if carry X has a reduced central fiber, then the Donaldson stack invariant can be decomposed into the summation of entropy and JKX plus delta energy, and non-Archimedean entropy can be denoted as this, where V is a restoration of order of E. So here, the row discrepancy appears. And now we can define adiabatic causability. So let F be a price algebraic fiber space pair. This means that so H is relatively ample over B, and so connected fibers. And this is called adiabatically K-semistable if X delta epsilon H plus L is K-semistable for sufficiently small epsilon, and uniformly adiabatically K-stable if there exists a positive delta such that the Donaldson stack invariant is bigger than or equal to delta J epsilon H plus L for any test configuration for X delta epsilon H plus L for sufficiently small epsilon. And here we remark that so this delta is independent from epsilon. And in the definition of adiabatic stems from the adiabatic limit argument that phi and Davan sectona applied. And we remark that by the fact that existence of CSC matrix implies K-semistability of polarized varieties, phi, Davan sectona, and Jianson proved adiabatic K-semistability of certain fibrations. And so we want to prove, so to state our main results, so we need the following notion of logistic stability. So XBTL is a logistic pair if XBL is a polarized log pair and T is a Q-line bundle on X. So then the logistic Donaldson stack invariant of carry X carry L, this is and so test configuration, this is a test configuration, is so logistic Donaldson stack invariant is the following n plus 1 dimensional intersection number. This is a summation of log Donaldson stack invariant and JT non-Archimedean energy. And so now we define XBTL is K-semistable if the Donaldson stack invariant is non-negative for any test configuration, and we can define uniform K-stability similarly. And if B equals to 0, log twist K-stability coincides with twist K-stability introduced by Davan. And so twisted K-stability appears in Davan-Ross theorem. Sorry. And so, and let us recall the chemical bundle formula of Ambro and Fitz-Gongyo. So let F be LC, so F is a LC trivial fibration if Kx plus delta is linearly equivalent to 0 over C and X delta is row canonical. And so we can define KLT trivial fibration similarly And so if F is a LC trivial vibration, then the chemical bundle formula holds as follows. So Kx plus delta is the product of this divisor. And here M is called the modular and B is the discriminant. And B is defined by multiplicity of B at P equal to 1 minus log chemical threshold of S star P. So this is the supremum of T such that X delta plus TF star P is LC at generic point of P. And P is codimension 1 point of C. And so Ambro and Fujino Gongyo proves the following. So for any LC trivial vibration, we can take good resolution phi such that so this is so induced sub LC trivial vibration so correspond to X delta. And so we can define similarly M prime moduli. So if C prime is good, so then M prime is nef and phi push M prime equal to M. And we will use this theorem. And so we can state our main results. So let F be a LC trivial vibration. So let M and B be the modular and the discriminant respectively. If F is adiabatically K-semi-stable, then CBML is K-semi-stable. So for trivial vibrations, this is a generalization of Durban-Ross theorems. And we obtain the following partial converse. So suppose further that F be a KT trivial vibration and C is a smooth curve. So then F is uniformly adiabatically K-stable if and only if CBML is uniformly K-stable. And so from now, we explain the proof of our theorems. So to prove theorem 1, so we need to recall the definition of the minimal model program. So let phi be a birational contraction and Kx plus delta equal to the push forward of Ky plus delta y. So then X delta is called a good minimal model if Kx plus delta is semi-ample and phi is Ky plus delta y negative. And X delta is called the log canonical model if Kx plus delta is ample and phi is Ky plus delta y non-positive. So this means that's all. There is a common resolution. So and so we can write E, and if Ky plus delta y non-positive, E is effective, and Ky plus delta y negative, E is effective and contains all 5 exceptional divisors. And so to prove our main theorem 1, we need the following techniques of the minimal model program proved by Heikon Shu. So let X delta be a DLT pair over a normal variety S. For that, there is an open subset U such that the restoration of X delta to U has a good minimal model, and any log canonical center of X delta intersects with U. then X delta also has a good minimum model. And now we prove our main theorems, our main theorem 1. So first, take a normal test configuration carry C, carry F for CL such that the Donaldson-Stark invariant is negative. And assume that there exists a chemical morphism rho C. And by taking a finite covering, so let Y be a semi-stable resolution of X times C over C, and assume that there exists a variational morphism G from Y to carry X times A1. And let pi Y be the chemical projection. And by chemical bundle formula, then we can write so Ky plus G inverse push delta A1 plus the summation of this equal to the product of these divisors, where B is the discriminant and M is the modular divisor. And by an easy computation, we can write so as follows, where F runs over horizontal exceptional divisors. So since theorem of Ambro and Fujino-Gongyo, so by taking good resolution, so M prime the moduli minus rho C tilde, rho C prime, product M times A1 is anti-effective by negativity lemma. So if so the push forward of this divisor is M minus rho C product M times A1. Thus, carry M decomposed into the summation. And so carry B has so multiplicity of so max max F one minus a XA1 delta A1 F. Here P is the component of carry C0, and F runs over component divisors dominated P. And so for this, so carry dy is effective over dimension 1 point of over C. And then take H prime, the stress transformation of H in Y, and take sufficiently small epsilon. Then Ky plus G inverse push delta A1 plus the summation of F plus epsilon H prime has a good minimum model over C set minus C0 by the argument of DLT modification. So if so now Ky plus the delta plus F has a good minimum model by the argument of Fujino. And so therefore, by the theorem of Heikon-Shu, so we obtain the log canonical model carry X carry H of Ky plus G plus push delta A1 plus the summation of F plus epsilon H prime over C entirely. And so this divisor contracted. And so carry H is extension of H times A1. And this is ample. So carry H plus M pi star L is so ample. We may assume that. So, and so for calculation of dy, so dy it contains no fibers. Thus, so the effective part of dy are contracted. So the symmetric transformation carry D on X has a spot of codimension more than 1 point over C. So we can compute as follows. So the Donaldson stack invariant. And so recall that so df Vm carry C carry L as Kc plus feedback M plus inverse B carry L B, and so B plus 1 B LB Kc plus M plus L sorry B LB minus 1 carry LB plus 1, and this term appears here. So we need to compare K carry X we want to compare so Kc plus rho push M plus rho inverse push B, where n equal to dimension of X and B equal to dimension B. And so by the formula, so we can compute it so as follows. So K carry X rho carry X inverse push delta P1 over P1. So rho carry X is so variation morphism, chemical variation morphism. And so this is the product of Roche product Kc times A1 plus M times A1. Sorry. Kc plus Roche product M times A1. And here, so we can compute as follows. So the Donaldson stack invariant, the leading coefficient of the Donaldson stack invariant is smaller than or equal to the Donaldson stack invariant of the base. So by the assumption, this Donaldson stack invariant is negative. Thus, for sufficiently large M, the Donaldson stack invariant of the fiber space is negative. Thus, we could prove the theorem. And to prove theorem 2, so we need to recall the definition of delta invariant. So for any divisorial variation V on X, so let X delta V be the log discrepancy, can be defined as prime divisors over X, and SLV equals to the inverse of volume L and integral of volume of L minus XV. And here we can define delta invariant as follows. So delta X delta L equal to the limit of the infimum or the log chemical threshold where D runs over n basis divisor of L. And this is and DI from a basis of H0 XML. And this is proved by Brown Johnson. So delta invariant equal to the infimum of X delta V over SLV, where V runs over any divisorial variation or variations. So here we can prove the following theorem. So let CBML be a log-test pair. Then delta CBL is bigger than or equal to the infimum of T, where H is bigger than or equal to TJL. And second, the first one is proved in smooth cases by Buxton Johnson. And so if L equal to minus KC plus B plus M, and M is semi-ample, the delta invariant is bigger than or equal to 1 if CBML is K-semi-stable. So this means that log twist is final. And so this theorem proved as ratio, Fujita, and Brown-Lear. So and we also proved the following convergence of the delta invariant of the total space to the one of the base curve adiabatically. So let F be a fibration such that the dimension of C equal to 1 and B the discriminant defined as log canonical trivial fibrations. So multiplicity of PB equal to 1 minus LCT P X delta F star P. And then the limit of delta X delta epsilon H plus L equal to delta CBL. And so for fiber surfaces, we can prove it as follows. So for any MVS divisor D, we can decompose D into the horizontal and vertical part, DH and DV. And we can check that DH has sufficiently small multiplicity on any point since DH.L is less than or equal to epsilon H.L. Thus, for sufficiently small epsilon, it's sufficient to calculate the log canonical threshold. But DV has multiplicity nearly equal to SLF for any vertical prime divisor. And we can calculate uniformly converge to this log canonical threshold. So this is very we can conclude that the limit of delta invariant converges to the base, the delta invariant of the base. And so now we can prove our main theorems. So suppose that C is a smooth curve. So the Calabrian vibration F is uniformly adiabatically K-stable if and only if CBML is uniformly K-stable when F is a K-related trivial vibration. And we remark that so Kc plus M plus B equals to Kc plus LCM. And if this is ample, the theorem follows from Jian-Song. And Kc plus LCM is numerically if Kc plus LCM is numerically equivalent, then Kx plus delta is also numerically equivalent. Thus, in this case, the theorem follows from the Odaka's result. Hence, we can conclude that it suffices to prove it when the base curve is longest Fano curve. So, and the only part followed from a slight modification of theorem 1 and the following proposition. So let CBML be a K-semi-stable but not K-stable longest Fano pair. Then there exists an effective Q divisor D such that C plus C B plus epsilon D ML is K unstable for sufficiently small epsilon. To prove this proposition, we use so longest beta invariant as Fujita introduced for log beta invariant. So assuming this, so if carry X, carry M, the Donaldson stack invariant is so uniformly positive, so then as theorem 1, so epsilon F star D, carry X, carry M is negative. But so this Donaldson stack invariant is uniformly positive. So this is ridiculous. Thus, we obtain the only part. And for if part, so let degree of B plus M equal to S, and assume that degree of L equal to 1. Then the limit of delta invariant coincides with the delta invariant of the base, and this coincides with delta CB minus Kc plus B plus M, and this delta invariant is bigger than 1 since CBML is longest K-stable. On the other hand, Kx plus delta is numerically equivalent to minus 2 minus S F star L, and by Gaussian theorem, so we can check that. So and this is NF and X epsilon H plus is just H stable. And hence we have Jkx plus delta carry X carry M is bigger than or equal to minus 2 minus S if J epsilon H plus L. And so we can conclude that. So the Donaldson stack invariant can be decomposed into HNA delta plus Jkx delta NA. And this is bigger than or equal to delta minus 2 minus S J epsilon H plus L. And so for sufficiently small epsilon, this invariant is uniformly positive. Thus, the vibration is uniformly K-stable, uniformly adiabatically K-stable. And we learned that so if delta equals to 0 and X is smooth, then x epsilon h plus L has a statistic metric by the result of Kuai-Yang. And we obtain other applications. So let us recall the following theorem of Jensen. So let F be a fibration over a curve such that Kx is ample. Then x epsilon Kx plus L has a statistic metric for sufficiently small epsilon. And we obtain the results on K-stability of fibrations with Kx relatively ample, but not Kx is ample. We need the following result on J-stability. This is proved in my first preprint. So let XL be a prime variety. So and H be a pseudo-effective divisor on X. So then XL is J semi-stable if and only if the cavity divisor is NF. And we obtain the following by the Roth theorem and convergence of delta invariant. So let L be a fibration over a curve such that Kx plus delta is relatively ample and the dimension of X equals to 2 if X delta is row canonical and Kc plus LCM is ample, then F is uniformly adiabatically K-stable. And second, if X delta is KLT and CB LCM minus B minus Kc plus LCM is wrong twist funnel where B is discriminant. And uniformly being stable. So this is modification of K-stability. So then F is uniformly adiabatically K-stable. And so if delta equals to 0 and X is smooth, existence of statistic metrics follows from results of Chili and Jiang. And finally, I would like to apply our main theorem to K-stability of rational surfaces and explain conjecture of Miranda on rational wire thrust fibrations. So let L be a smooth rational surface. So let us recall the following basic fact. So the first one, X has at most one multiple fiber. And second, if X has no multiple fiber, then it has a section S. Let W be the relative canonical model XS and call this the wire thrust model. So this looks like so singular fiber, and so these are minus 2 curve, and so we contract, and this is wire thrust fibration, and this has diverse singularities. In this case, it's a singularity. And by Miranda, it is known that GLT stability of rational surfaces without no multiple fiber correspond to what singular fiber X has. So he studied GLT stability of cubic pencil in P2 or rational wire stress fibrations. And he realized that so GIT stability of rational surfaces depends on what singular and so we obtained the following corollary by applying our main results. So let X be a smooth rational surface, S be a relatively ample divisor over P1, and M be the multiplicity of a unique multiple fiber. So XS is uniformly adiabatically K-stable and have statistic metrics if and only if one of the following holds. So the first one, m equal to 1 and x has at most reduced fibers. So no iron star fiber, 2 star, 3 star, or 4 star fiber. Or m equal to, and x has no 2 star or 3 star fiber. And if m equal to 3 and x has no 2 star fiber, and m is bigger than 3. And xs is adiabatically k-unstable if one of the following holds. So m equal to 1 and x admits one of 2 star, 3 star, or 4 star type fibers. Or m equal to 2 and x admits a 2 star type fiber. And so these conditions are equivalent to K-stability of log-twisted K-stability of the base curve P1. And these conditions are equivalent to log-twisted K stability of P1. Thus, so we obtain the corollary by our main theorems 1 and 2. And so adiabatic uniform adiabatic K-stability depends on what singular fiber X has. And so Miranda conjectures the following. So let WH be applied rational wire source fibration if W has at least 1 2 star, 3 star, 4 star type fiber, then WH is asymptotically unstable and at most reduced or iron star type fiber, then WH is asymptotically semi-stable. And this notion is derived from GIT. And asymptotic semi-stability implies K-semi-stability. It is an easy fact. And so we use by comparing the weight of CM line model and GIT stability and the chemical bundle formula. So we obtain the following theorem. So let WS be a rational wire source vibration with a section S and L equal to OP1. Then the following hold. The first one, if W has at least 1 2 star, 3 star, or 4 star type fiber, then WAS plus L is K unstable for A. So this implies asymptotic Chow instability. And for the second case, if W has at least 1 iron star type fiber for some positive n, then WAS plus L is asymptotically Chow unstable for sufficiently small a. So for the first one, so if the Picard number equal to or W has 2 star fiber, so any polarization is the form of this. Thus, so we can conclude that the Miranda's conjecture first holds for rational wire source vibrations with the Picard number 2. And for the second, so there exists at least a rational wire source vibration with at least 1 iron star type fiber for some positive n, but no 2-star, 3-star, or 4-star fiber. And for 72, WAS plus SL is asymptotically unstable for sufficiently small a. Thus, so the Miranda's conjecture second does not hold in general. Thank you for listening. Thank you for organization.
Okay, thank you very much. So any questions and comments?
I have a question.
Okay, go ahead.
I'm sorry, just let me just turn on my camera. Hi, I'm Masafumi. Thank you very much for your talk. I really enjoy it. So I have maybe two questions about slide 29.
29?
Yes. So the first question is that can you maybe say something about how the multiplicity of the multiple fiber appears in your results, and also so when we have multiple fiber, the surfaces they also come from pencils, certain pencils in the plane. So I was curious whether you consider somehow what these pencils look like. Yeah, so this is the first question. And then the second question is about Miranda's conjecture. There's also another part for the conjecture, right? So if we have just reduced fibers, then the conjecture is that for any polarization, we would have Shao stability. So have you also considered that?
So sorry, I couldn't catch you. So for the first one, pencil. So I catch only the word. So
right. So when we have a rational elliptic surface with a multiple fiber, they also come from certain pencils in the plane. And I was wondering whether you had thought about that, if that somehow plays a role in your result, or how exactly like the multiplicity is appearing.
In a case with multiple fiber or not?
Yes, in the case with multiple fiber, yes. Yeah.
Multiple fiber, and fiber with so for 3-ion case, so GIT stability. Your question is this, so no.
I think you asked your question was like if he related his, I mean he related the pencils question.
Yeah, if he considered the pencils in the plane that give rise to the surfaces on when m is not bigger than 1, right? Because in slide 29, he has results for m equals 2, m equals 3, and m bigger or equal than 4, right? And he's relating the K stability in terms of the singular fibers. And usually, so these singular fibers are going to come from special curves in the plane. So I just wonder whether he thought about that or not.
Mm-hmm. So you mean pencils of these cubics, right?
No, so it's going to be a pencil of curves of degree 3m. So these are called half-m pencils.
I see.
Yeah.
So
Can you see the page 29? Yeah.
29.
Yep.
Sorry.
So
Yeah.
Hattori-kun, the question is like if you consider something called Harfen pencil, and if you related that to your study. Do you know that? Do you know this Harfen pencil? And
ハルフェンペンシルと関連付けたっていうことですか？
ハルフェンペンシルというものと関係するんじゃないかということを聞いて、それを考えたかと。
ああ、
ハルフェン、someone's name, right?
Yes, it's French, so my pronunciation is very poor. I'm sorry.
ハルフェン、yes. Yeah.
そう、
Perhaps not, right?
I have not.
It's okay.
I have
I
not
was just
thought
curious.
about this, but I'm curious about your as your study, so Harfen pencil or so.
Yeah, so this is part of my PhD thesis. So I described the GIST stability for these pencils as points in the space of all pencils of SASTIX, for instance, in the m equals 2 case. And like I have, if I remember correctly, like the unstable ones are the ones that correspond to 2-star fiber, which seems to be somehow compatible with what is written here in this slide. So I'm very curious about this.
I see.
Yeah.
I see.
Yeah. Yeah, and then if it's okay, that, like the other question was just about Miranda's conjecture. Like there's 3 parts in the conjecture, and then there's 1 part missing, right?
Ah,
Yeah, have you thought about the other part, like when we have just reduced fibers?
so missing conjecture is so your question is I sorry. As the most reduced most reduced fiber, if and only if so. But so for this conjecture, I have no idea about this. So for to prove Chawan stability, so we only have to check there is about lambda, so the weight is negative. But for missing conjecture, so we have to prove for any GM one parameter subgroup, so the weight is positive. So this is so difficult.
Okay, so any other questions, comments?
Yeah, perhaps about the first question, maybe we can discuss later.
Okay. All right, so I think no more questions. So, all right, so thank you for your talk, and thank all of you for coming. All right, so you have a good day and you have a good night. All right, so let me close the this session. All right, bye. Thank you.
Thank you, Ji-hoon.